Hi there. Today we're looking at Attention is All You Need by Google. Just to declare, I don't work for Google just because we've been looking at Google papers lately. But it's just an interesting paper and we're going to see what's the deal with it. So basically what the authors are saying is we should kind of get away from basically RNNs. So traditionally what you would do, and these authors particularly are interested in NLP, natural language processing. So traditionally when you had like a language task, like the cat eats the mouse, and you'd like to translate this to, say, any other language, like let's say German or whatever, what you would do is you would try to encode this sentence into a representation and then decode it again. So somehow this sentence needs to all go into, say, one vector, and then this one vector needs to somehow be transformed into the target language. So these are traditionally called sec-to-sec tasks, and they have been solved so far using recurrent neural networks. You might know the LSTM networks that are very popular for these tasks. What basically happens in an RNN is that you go over the, say, source sentence here, one by one. Here, you take the word the, you kind of encode it, maybe with a word vector, if you know what that is. So you turn it into like a vector, a word vector, and then you use a neural network to turn this vector into what we call a hidden state. So this H0 is a hidden state. You then take the second token, here cat. You again take its word vector, because you need to represent it with numbers somehow. So you use word vectors for that. You turn this into, you put it through the same function. So here is what's like a little e for encoder. You turn it into the same function, but this time this hidden state also gets plugged in here. So the word vector, the hidden state. You can actually think of having like a start hidden state here, H start. Usually people either learn this or just initialize with zeros. That kind of goes in to the encoder function. So it's always really the same function. And from the previous hidden state and the current word vector, the encoder again predicts another hidden state, H1, and so on. So you take the next token, you turn it into a word vector, you put it through this little e encoder function, and of course this is a lot more complicated in actual, like, say, an LSTM, but it's the basic principle behind it. So you end up with H2, and here you'd have H3, H4. And the last hidden state, H4 here, you would use this in kind of exactly the same fashion. You would plug it into like a decoder, a little D decoder, which would output you a word, D, and it would also output you a next hidden state, so H5. Let's say, let's just go on with the listing of the states, and this H5 would again go into the decoder, which would output Katze. Like, so that's how you would decode. You basically, these RNNs, what they do is they kind of take, if you look on top here, they take an input, a current input, and they take the last hidden state, and they compute a new hidden state. In the case of the decoder, they take the hidden state and they take kind of the previous, usually the previous word that you output, you also feed this back into the decoder, and they will output the next word. It kind of makes sense. So you would guess that the hidden state kind of encodes what the sentence means, and the last word that you output, you need this because maybe for grammar, right? You know what you've just output, so kind of the next word should be based on that. Of course, you don't have to do it exactly this way, but that's kind of what these RNNs did. So attention is a mechanism here to basically increase the performance of the RNNs. So what attention would do is, in this particular case, if we look at the decoder here, if it's trying to predict this word for cat, then, or the next word here, say here it wants the next word. And in essence, the only H6, the only information it really has is what the last word was, like German word for cat, and what the hidden state is. So if we look at what word it actually should output in the input sentence, it's this here, eats, right? And if we look at kind of the information flow that this word has to travel, so first it needs to encode into a word vector, it needs to go through this encoder. That's the same function for all the words, so nothing specific can be learned to the word eats here, right? It needs to go through this hidden state, traverse again into another step, this hidden state, because we have 2 more tokens, and then the next hidden state. And then it goes all the way to the decoder, where the first 2 words are decoded, and still, so this H6, this hidden state, somehow still needs to retain the information that now the word eats somehow is kind of the word to be translated, and that the decoder should find the German word for that. So that's of course a very long path. There's a lot of transformations involved over all of these hidden states. And the hidden states, not only do they need to remember this particular word, but all of the words and the order and so on, and the grammar. The grammar you can actually learn with the decoders themselves, but kind of the meaning and the structure of the sentence. So it's very hard for an RNN to learn all of this, what we call long-range dependencies. And so naturally you actually think, well, why can't we just, decode the first word to the first word, the second word to the second word? It actually works pretty well in this example, right? Like the D, cat, katze, eats. We could just decode one by one, but of course that's not how translation works. In translations, the sentences can become rearranged in the target language, like one word can become many words, or it could even be an entirely different expression. So attention is a mechanism by which this decoder here in this step that we're looking at can actually decide to go back and look at particular parts of the input, especially what it would do in like popular attention mechanisms is that this decoder here can decide to attend to the hidden states of the input sentence. What that means is, in this particular case, we would like to teach the decoder somehow that, look here, I need to pay close attention to this step here, because that was the step when the word eats was just encoded. So it probably has a lot of information about what I would like to do right now, namely translate this word eats. So this mechanism allows, so if you look at the information flow, it goes through, this word vector goes through one encoding step and then is at the hidden state, and then the decoder can look directly at that. So the path length of information is much shorter than going through all of the hidden states in a traditional way. So that's where attention helps. And the way that the decoder decides what to look at is like a kind of an addressing scheme. You may know it from neural Turing machines or kind of other kind of neural algorithms things. So what the decoder would do is in each step it would output a bunch of keys. Oops, sorry about that. That's my hand being trippy. So what it would output is a bunch of keys. So K1 through Kn. And what these keys would do is they would index these hidden states via a kind of a softmax architecture. And we're gonna look at this, I think, in the actual paper we're discussing, because it's gonna become more clear. But just kind of notice that the decoder here can decide to attend to the input sentence and kind of draw information directly from there, instead of having to go just to the hidden state it's provided with. So if we go to the paper here, what do these authors propose? And the thing is, they ditch the RNNs. They basically say attention is all you need. You don't need the entire recurrent things. Basically, in every step of this basically of the decoding, so you want to produce the target sentence. So in this step, in this step, in this step, you can basically, you don't need the recurrence. You can just kind of do attention over everything, and it will be fine. Namely, what they do is they propose this transformer architecture. So what does it do? It has two parts, what's called an encoder and a decoder, but don't kind of be confused, because this all happens at once. So this is not an RNN, it all happens at once. All the source sentence, so if we again have the cat, oops, that doesn't work as easy. Let's just do this. This is a source sentence. And then we also have a target sentence that maybe we've produced 2 words and we want to produce this third word here. I want to produce this. So we would feed the entire source sentence and also the target sentence we've produced so far to this network. Namely, the source sentence would go into this part, and the target that we've produced so far would go into this part. And this is then all combined, and at the end we get an output here at the output probabilities that kind of tells us the probabilities for the next word. So we can choose the top probability and then repeat the entire process. So basically every step in production is one training sample. Every step in producing a sentence. Here before with the RNNs, the entire sentence to sentence translation is one sample, because we need to back propagate through all of these RNN steps because they all happen kind of in sequence. Here basically output of one single token is one sample, and then the computation is finished. The backprop happens through everything only for this one step. So there's no multi-step kind of backpropagation as in RNNs. And this is kind of a paradigm shift in sequence processing, because people were always convinced that you kind of need these recurrent things in order to make good, to learn these dependencies. But here they basically say, no, we can just do attention over everything, and it'll actually be fine if we just do one-step predictions. So let's go one by one. So here we have an input embedding and say an output embedding. These are symmetrical. So basically the tokens just get embedded with, say, word vectors again. Then there's a positional encoding. This is kind of a special thing where, because you now lose this kind of sequence nature of your algorithm, you kind of need to encode where the words are that you push through the network. So the network kind of knows, this is a word at the beginning of the sentence, or this is a word towards the end of the sentence, or that it can compare two words, like which one comes first, which one comes second. And you do this, it's pretty easy for the networks if you do it with kind of these trigonometric functioning embeddings. So if I draw you a sine wave, and I draw you a sine wave of that is double as fast, and I draw you a sine wave that is even faster, maybe this one actually sync 1 2 3 4 5, nah, it doesn't matter, you know what I mean. So I can encode the first word, I can encode the first position with all down, and then the second position is kind of down down up, and the third position is kind of up, down, and so on. So this is kind of a continuous way of binary encoding of position. So if I want to compare two words, I can just look at all the scales of these things, and I know, aha, this word, one word is high here and the other word is low here, so they must be pretty far away. Like one must be at the beginning and one must be at the end. If they happen to match in this long wave, and they also are both kind of low on this wave, and then I can look in this wave for like, oh, maybe they're close together, but here I really get the information which one's first, which one's second. So these are kind of positional encodings. They're not critical to this algorithm, but they just encode where the words are, which of course that is important, and it gives the network a significant boost in performance. But it's not like, it's not the meat of the thing. The meat of the thing is that now that these encodings go into the networks, they simply do what they call attention here, and attention here. So there's kind of three kinds of attention. So basically the first attention on the bottom left is simply attention, as you can see, over the input sentence. So I told you before, you need to take this input sentence, if you look over here, and you somehow need to encode it into a hidden representation. And this now looks much more like the picture I drew here, and the picture I drew right at the beginning is that all at once you kind of put together this hidden representation. And all you do is you use attention over the input sequence, which basically means you kind of pick and choose which words you look at more or less. So with the bottom right, so in the output sentence that you've produced so far, you simply encode it into kind of a hidden state. And then the third on the top right, that's sorry I got interrupted. So as I was saying, the top right is the most interesting part of the attention mechanism here, where basically it unites the kind of encoder part with the kind of it combines the source sentence with the target sentence that you've produced so far. So as you can see, maybe here I can just, that's slightly annoying, but I'm just gonna remove these kind of circles here. So if you can see here, there's an output going from the part that encodes the source sentence, and it goes into this multi-head attention. There's two connections, and there's also one connection coming from the encoded output so far here. And so there's three connections going into this, and we're gonna take a look at what these three connections are. So the three connections here basically are the keys, values, and queries. If you see here, the values and the keys are what is output by the encoding part of the source sentence, and the query is output by the encoding part of the target sentence. And these are not only one value, key, and query, so there are many in this kind of multi-head attention fashion. So there are just many of them instead of one, but you can think of as just kind of sets. So the attention computed here is, what does it do? So first of all, it calculates a dot product of the keys and the queries, and then it does a softmax over this, and then it multiplies it by the values. So what does this do? If you dot product the keys and the queries, what you would get is, so as you know, if you have two vectors and their dot product basically gives you the angle between the vectors. With, especially in high dimensions, most vectors are going to be of kind of a 90-degree kind of, oh, I know the Americans do the little square. so most vectors are going to be not aligned very well, so their dot product will kind of be zero-ish. But if a key in the query actually align with each other, like if they point into the same directions, their dot product will actually be large. So what you can think of this as, the keys are kind of here. The keys are just a bunch of vectors in space, and each key has an associated value. So each key, there is kind of a table, value 1, value 2, value 3. This is really annoying if I do this over text, right? So again here, so we have a bunch of keys, right, in space, and we have a table with values, and each key here corresponds to a value. Value 1, value 2, value 3, value 4. So each key is associated with one of these values. And then when we introduce a query, what can it do? So a query will be a vector like this. And we simply compute so this is Q, this is the query. We compute the dot product with each of the keys. And then we compute a softmax over this, which means that one key will basically be selected. So in this case, it would be probably this blue key here that has the biggest dot product with the query. So this is key 2 in this case. And the softmax, so if you don't know what a softmax is, if you have like x1 to xn be like some numbers, then you simply do you map them to the exponential function, each one of them, but also each one of them you divide by the sum of over I of e to the xi. So basically, this is a renormalization. Basically, you do the exponential function of the numbers, which of course this makes the kind of big numbers even bigger. So basically, what you end up with is one of these numbers, x1 to xn, will become very big compared to the others, and then you renormalize. So basically one of them will be almost 1 and the other ones will be almost 0. Simply the maximum function you can think of in a differentiable way. I mean, you just want to select the biggest entry. In this case here, we kind of select the key that aligns most with the query, which in this case would be key 2. And then when we multiply this softmax thing with the values, so this query, this inner product, if we multiply Q with K2 as an inner product, and we take the softmax over it, softmax, what we'll do is, I'm going to draw it upwards here, we're going to induce a distribution like this. And if we multiply this by the value, it will basically select value 2. So this is kind of an indexing scheme into this memory of values, and this is what then the network uses to compute further things. So you see the output here goes into kind of more layers of the neural network upwards. So basically, what you can think, what does this mean? You can think of, here's the whoopsteep. I want to delete this. Here, you can think of this as basically the encoder of the source sentence, right here. Discovers interesting things. That looks ugly. It discovers interesting things about the source sentence, and it builds key value pairs. And then the encoder of the target sentence builds the queries. And together they give you kind of the next signal. So it means that the network basically says, here's a bunch of things. Here's a bunch of things about the source sentence that you might find interesting. That's the values. And the keys are ways to index the values. So it says, here's a bunch of things that are interesting, which are the values, and here is how you would address these things, which is the keys. And then the other part of the network builds the queries. It says, I would like to know certain things. So think of the value as like attributes, like here is the name and the kind of tallness and the weight of a person, right? And the keys are like the actual indexes, like name, height, weight. And then the other part of the network can decide, what do I want? I actually want the name. So my query is the name. It will be aligned with the key name, and the corresponding value would be the name of the person you would like to describe. So that's how kind of these networks work together. And I think it's a pretty ingenious. It's not entirely new because it has been done, of course, before with all the differentiable Turing machines and whatnot. But it's pretty cool that this actually works, and actually works kind of better than RNNs if you simply do this. So they describe a bunch of other things here. I don't think they're too important. Basically, the point that they make about this attention is that it reduces path lengths, and kind of that's the main reason why it should work better. With this entire attention mechanism, you reduce the amount of computation steps that information has to flow from one point in the network to another, and that's what brings the major improvement, because all the computation steps can make you lose information, and you don't want that. You want short path lengths, and so that's what this method achieves, and they claim that's why it's better and it works so well. So they have experiments. You can look at them. They're really good at everything. Of course, you always have state of the art. And I think I will conclude here. If you want to check it out yourself, they have extensive code on GitHub where you can build your own transformer networks. And with that, have a nice day and see ya.